welcome everybody. So far we've talked about how the potential energy diagram looks, how to measure activation energy, all that good stuff. So now we're going to talk about how a catalyst will affect the reaction rate and also how a catalyst will affect the diagram as well. And so a catalyst, the key terms that you need to know, and we kind of went over this when we were talking about collision theory, the first thing about a catalyst is that it speeds up the reaction rate. So we have an increase in the reaction rate. So the rate of the reaction will get bigger, get larger. And the second thing that you have to know is that a catalyst will lower the activation energy. And so the activation energy will get lower for the reaction. So what does this look like on a graph? Well, we could do this for endo or exothermic. If I do an exothermic graph here, actually let me make that a little bit higher activation energy just to show you. So here's our exothermic reaction. If I were to put in the effect of a catalyst there, I would have a smaller activation energy. So I could draw this in like this. And so this would be my catalyzed reaction. And so if we were to go ahead and show the differences in activation energies, if I have my first activation energy here versus my second activation energy here, for the uncatalyzed, if we do that in blue to be consistent, we would have an activation energy there. And if we were to do the reverse activation energy, that would again be right here. Now if we were to show in red what the catalyzed reaction looks like, the forward activation energy would be lower here, and the reverse would be lower there. In both cases, you can see that the red catalyzed activation energy is lower. So those arrows on the graph will be lower. Now sometimes they use this language for the catalysts where they say that they provide an alternate pathway for the reaction. And what they mean by that is that if I were to go ahead and draw out a potential energy diagram, that I could have a catalyst actually providing what's known as a different mechanism, a different way of going about the reaction. And sometimes you'll see something like this, where you'll have, start over again, zoom in here, or you have something like this. And notice in this case, I have a new pathway, and it has now two different peaks. And these different peaks represent, this peak right here, 1 and 2. Peaks 1 and 2 represent separate steps in the reaction. And so now we have a two-step reaction, but it still is going to be quicker than the one-step reaction because those two steps both are lower activation energy. And the analogy I like to use for catalysts and these diagrams, it's kind of like a shortcut. So, like we have the uncatalyzed reactions in blue, and that would be like if somebody were to say, here you are starting on the left for the reactants, and you have to get to the products, and you have to go up this hill in order to get there. And reaction in red, the catalyzed reaction, that's taking a shortcut. You're kind of cutting out that big hill that you'd have to go over in order to get from the reactants to the products. Okay, so this is how a catalyst affects a reaction rate, how it relates to the potential energy diagrams. This comes up quite a bit. They want you to be able to draw that in. One last thing about this before I move on, and that is notice where I started and ended the catalyst pathway. I didn't start it below the reactants or above the products. I had it blend in there. And that's really key because the delta H for these reactions, they're unaffected. The difference, and if I do that in a different color here so there's no confusion, but if I look here at the reactants and the products, the delta H hasn't changed. And that's important to take note that that will not happen. The delta H will not change when your reactions catalyze. Okay, one last thing I want to do with you is a table I from the reference table. And this table tells you about different reactions at a certain temperature and pressure, which are pretty much not STP, but close to it. The temperature is a little bit higher. That's pretty much room temperature. And so they give you a different class of reactions. The first class of reactions that they show you are combustion reactions, which we'll do in red here. So these combustion reactions all produce CO2 and H2O. Next, they do a whole bunch of, and actually this also is included there too, it is a combustion, except there's no hydrogen, so you're not producing H2O. The next class of reactions that they do are synthesis reactions, and those are a bulk of them, and those go all the way down here, these next bunch of reactions, all the way down to where HI is. And all of those are synthesis reactions. So these are synthesis reactions. And then you have reactions where they dissolve a substance in water, and that would be these reactions here. Oops. That would be these reactions here where you're dissolving in water. And you can see that all of these reactions have a delta H, either positive or negative. And they're so nice, they tell you minus sign for delta H. That tells you that it's exothermic, and that's what they're showing you. And so depending on the type of reaction will depend on if it's exothermic or endothermic. Something else that's kind of cool about this is that they can do a little bit of stoichiometry here. Like take, for example, the reaction that forms NH3. So we have N2 plus 3H2 yields 2NH3. Well, what if they want it for 1 mole of NH3? Well, for 2 moles of NH3, it's about minus 92 kilojoules. So if I want for 1 mole, I simply cut it in half, and that would give me then 92 divided by 2, that would be 46 kilojoules. And so you'll see this a lot. They'll change the coefficients and expect you to change the delta H accordingly, and you have to be able to do that. Another thing that comes up is the phase. And you can see here that there's 2 reactions for forming water. There's this reaction, and they're different only in their phase. And sometimes they'll say, like, how much heat is released when 1 mole of liquid water or 1 mole of gaseous water. And so you have to look really carefully on this chart and not get fooled and pick the wrong one. Okay, the last set of reactions in blue here are dissolving in water. And they like this question that goes along with this. And the question sort of sounds like the following. They'll say, when you dissolve substance, whatever, in water, and it'll be one of the ones on the chart, what happens to the temperature of the water? And the trick is this, and this is where you have to be careful. When there is a negative delta H, that releases heat. And that release in heat will actually make the temperature go up. And the reason why I bring this up is because people see the negative delta H and they're like, oh, yeah, it's absorbing, or negative delta H, it's getting colder, it's negative. But it's actually the opposite. So when you have a positive delta H, you absorb heat. And so that will lead to a decrease in temperature. So that's where we're at with these particular types of reactions and how to read this chart. So the next thing that we'll do, and we're not going to do it today, we'll talk about heat of summation, and this is really a big part of the chapter. This is what goes on to the honors section of the chapter. So far, everything that we've done has all been about Regents chemistry. The next section will be the honors stuff. All right, thanks so much for watching, and hope you enjoy.